One paper written by one man almost 90 years ago changed the course of history. Alan Turing, an individual you may have seen portrayed in the movie The Imitation Game, working with the brightest minds in England, building a machine to crack the Germans' Enigma code, serving as a turning point in World War II, ultimately saving millions of lives. But 5 years prior, in 1936, he would go on to write a paper that changed the course of history, titled On Computable Numbers with an Application to the Entscheidungsproblem, laying the theoretical foundation of modern computing. Today, I'm going to tell you the story of how Alan Turing's groundbreaking 1936 paper on computable numbers and the concept of the universal machine, now known as the Turing machine, revolutionized the field of computer science and ultimately led to the development of many technologies that have changed the world as we know it. In the mid-1930s, a young Alan Turing sat at his small office at Princeton University, surrounded by stacks of papers and books. He had been working tirelessly on a problem that had puzzled mathematicians and logicians for decades, the Entscheidungsproblem, or the decision problem. The decision problem is a question of mathematical logic that asks whether there exists a method or algorithm that can determine whether any given statement in a formal system is true or false. In other words, it is asking whether the formal system is decidable. Although I must exclaim before we go any further that technically, Entscheidungsproblem, while it is German for decision problem, is not the same. It's considered to be a special case of the decision problem, a subcategory, if you will, while the decision problem is a general concept that encompasses not only Entscheidungsproblem, but also a wide range of other problems. A little bit annoying, but as many others do, I have found myself using these two terms interchangeably. I've tried to be accurate in this video, but keep that in mind. Anyway, an example. Consider the formal system of arithmetic. The decision problem for this system would be to determine whether there exists an algorithm that can take any statement in the system, such as 3 plus 4 equals 7 or 5 times 8 equals 40, and determine if it is true or false. In other words, the decision problem is asking if there's a way to always know if the answer is correct or not, no matter what math problem it's given. I want to emphasize the decision problem is a question of mathematical logic. It is not directly related to determining the truth of mathematical statements, but on the ability of the system of logic to decide whether any given statement in the system is true or false, whether it can be solved. If such an algorithm exists, the system is said to be decidable. Otherwise, it's undecidable. Many great minds had attempted to solve the problem but had come up short, such as the man who posed the Entscheidungsproblem in 1928, David Hilbert, and the man who provided a proof for the insolvability of the Entscheidungsproblem for a specific formal system known as Ackermann's system in the same year, Wilhelm Ackermann. That proof was later used by Alan Turing in this paper. And although they came up short, with the progress they made, Turing was determined to find a solution. He began by formulating a mathematical model of computation, which he called the universal machine. This machine, now known as the Turing machine, was a theoretical machine that could perform any calculation that could be expressed as an algorithm. The idea of the Turing machine was that it could read and write symbols on a tape, and move the tape left and right based on a set of rules. This theoretical machine was first introduced by Alan Turing in this 1936 paper. And while the paper itself was well received by the mathematical community, at the time it was written and published, the ideas laid out in the paper were not widely understood. By some of the early critics, it was actually seen as nothing more than an abstract idea with no practical application. But Turing saw the potential of his theoretical machine and knew that one day it could be used for much more than just solving mathematical problems. He proposed that if the negation of what Gödel has shown had been proved, i.e. if for each u, either u or negative u is provable, then we should have an immediate solution of the Entscheidungsproblem. For we can invent a machine which will prove consecutively all provable formulae. Sooner or later, it will reach either u or negative u. If it reaches u, then we know that u is provable. If it reaches negative u, then since k is consistent, we know that u is not provable. This statement says that if the negation of what Gödel had shown in his incompleteness theorems were true, then we would have a definitive answer to Entscheidungsproblem. Kurt Gödel's incompleteness theorem is considered one of the greatest intellectual achievements of the time. The theorem states that in any formal system powerful enough to express the basic laws of arithmetic, there will be statements that cannot be proved either true or false within the system, and there will always be true statements that cannot be proved. Turing showed that any problem that can be solved by an algorithm can be solved by a Turing machine, and that there are some problems that are unsolvable by a Turing machine, which implies that these problems are also unsolvable by any other algorithm or mechanical process. And with that, Turing used his theoretical machine to prove that Entscheidung's problem, which is the problem of determining whether a given statement in a formal language is true or false, is undecidable. However, this led to another question. Was there any statement for which the machine would never halt? This stems from the aforementioned negation of the well-known results that Gödel had shown, which was, in the formalism of Principia Mathematica, there are propositions U such that neither U nor negative U is provable. And thus, Turing reduced the Entscheidung's problem to a new one, the halting problem. And like Entscheidung's problem, the halting problem is also a special case of the decision problem. The halting problem is a problem of determining for a given computer program and input whether the program will halt or continue running indefinitely. For example, consider a computer program written in a programming language such as Python that takes an input and performs some calculation. The program could be something as simple as this. This program takes a single input, an integer x, and prints out the numbers from 0 to x minus 1. The halting problem is the question of whether, given the description of the program and input, such as my program 5 being x, it is possible to determine whether the program will eventually halt, i.e. stop running, or continue running indefinitely, i.e. loop forever on that input. In this case, the program will halt, as it is running a finite loop, and it will stop after the xth iteration. However, the halting problem asks if there is a general method that can be used to determine whether any given program will halt or not, regardless of the specific program or input. And in this paper, Turing proved that not only is the Entscheidung's problem undecidable, but that the halting problem is undecidable as well, meaning it cannot be solved with an algorithm. He showed that for any attempt to build such an algorithm, there would always exist a statement for which the algorithm could not be determined if the statement is true or false. This realization was a major breakthrough in the field of computability theory, and gave a mathematical framework for the understanding of the limits of what computers can do. Turing's ideas were further developed by other logicians and mathematicians, such as Alonzo Church, who independently proposed a similar concept of a universal machine in the same year Turing did, and was actually Turing's PhD advisor at Princeton. These ideas eventually led to the development of the Church-Turing thesis, which states that any computation that can be performed by a human can also be performed by a Turing machine. Turing's work on the Entscheidung's problem and the halting problem and the Turing machine has had a lasting impact on the field of computer science and mathematics. His ideas continue to shape our understanding of the limits of what computers can do and have influenced research in fields such as artificial intelligence, computational complexity, and theoretical computer science. Even today, his work in these areas continue to be a guiding light for researchers. He laid the foundation for the development of modern computers and paved a way for a plethora of technological advancements that have changed the world as we know it. From the way we communicate, to the way we conduct business, to the way we entertain ourselves. We all owe a debt to the groundbreaking research of Alan Turing and the concept of the universal Turing machine that was first introduced in this 1936 paper on computable numbers with an application to the Entscheidung's problem. Today, as we reflect on the legacy of Alan Turing and his revolutionary paper, we can't help but marvel at the impact that one man's idea can have on the world. It serves as a reminder that sometimes the greatest ideas are the ones that seem the most impossible, and that one person can truly make a difference.